okay. That is the following. Question. If going from straight to coily is favored, why doesn't it snap in your hand? Right? So, sure, I'm saying that this is unstable. Right? It really kind of, in our wanting way, it wants to be coiled. Why doesn't it coil? How come I can keep it there for as long as I like? It's not going to coil. Why doesn't it coil? Or what does it need to do? What do you need to do to get it to snap? Yeah. It need another force. And what exactly do you have to do to get it to snap? What's the trick? Yeah. You put a little bit of energy into it. Specifically, even we're not talking just talking physically. What do you do? What do you got to do to get it to snap? You agitate, or even I'm fishing. I know. Here we go. What I'm after, which is true of all these things, is you have to kink it. You have to put a little pinch in it. Once you start it bending, right? Here it is, this unstable state. What I do is I put a little kink in it, and once you put a little kink in it, the whole thing snaps. If you feel so, like if you pinch it between your fingers like this. But you can't see with my fingers, but I'm basically going like that to it. You'll find it goes boink and snaps. All right, so you got to put a little kink in it. Yeah, and exactly, you got to put a little bit of energy into it. So my question is the following. So you need to put a kink in it. All right, you got to start it off. So, therefore, there's a third transient state. What do I mean by transient? You cannot keep it in that kink state. It will. You cannot. It will snap on you, right? You can't. It only stays in that kink state for a split second. All right. So that's what I mean by transient. All right. It's a transient, third transient state. We'll call it kinked, and I'll draw it as that sort of shape. So where on the chart? All right. So my question is to talk to your neighbor about. I'm going to redraw this chart with the straight and the coily. Where does kinked go on that chart? And not only left to right, but up and down. Given what we've said about how these diagrams work, and given what we said about putting some energy in to put that little bit of a kink in it, where does it belong on that chart? So while you guys are talking, I'll redraw the chart. So it's high and low, and it's PE. And we've got... So while you guys are talking, here, let me pass this up the end, and people can put them in the bin because I'm going to need them back for what I want to do in a second. So, or actually, pass it up the end. I think what we'll do is we'll send. No, actually, I'm sorry, you guys. If you could straighten them out and put them in the bin. I'm going to send it up the aisle, and then I'm going to send it down the other side. So, yeah, if you can. You may have to get out of your seats if you don't mind, because I actually need them for what I want to show next. But anyway, while that's happening, think about and talk to your neighbor. Where does that kinked state go? No, put them all back. No, I need it now. I'm sorry. I got them all back. Yeah. I need a good number. Sorry. All right. Well, that's going around. Get a consensus, and we'll get down to business. I guess what I can do is you can pick an axis, and then where you want to go with that. The first person gets it easy, second person harder. All right, so Melanie Santos. Melanie, are you here? Melanie. All right. So, do you want to do left, right, or up, down? All right, left, right. So tell me, where on the left, right? Yes, it's going to be past the straight one, but before the coily one. So it's in the middle here. Because why? Exactly, because it's in between. It's neither completely straight nor completely coily. You have to go through the kinked version to get either way you go. Oh, I lost mine. Either way you go. To go from straight to coily, you got to kink it. And in the middle, from coily to straight, there's a kink state. Right? So it's got to be in the middle, left to right. All right, Melanie, thank you. So it's got to be in the middle. All right. Let me do another one for up, down. So Sandra, win. Sandra, are you here? Sandra. So up and down, where is it going to be? Up. Okay, so above coily? Above straight. Okay, because why? Well, let's leave activation energy for the moment out, but so it's a higher, or you said a higher energy. So why is it higher energy than straight? How do you know that it's higher energy than straight? It was what somebody said. That's cool. Someone said it. You put energy in. So straight is here. I had to put some energy in. Right? I had to put some extra potential energy into it. So that's exactly why. It's up from there because you put energy in. Like you were saying, you put activation energy in, which is actually the right word. I wanted to dodge that for the moment, but thank you. So where you want to be, it's up. Right? So it's in between because it's in between state-wise, and it's above the straight one because you had to put some energy in. Questions about how we got there? All right. So what Sandra said, or was Melanie, I'm sorry, I've mixed up people's names. So what I'm going to draw here, so this is you put in 2 kink. All right? And then you get out energy of the snap. All right, cool. So there's some really important terms, which actually were mentioned just a second ago in what you were talking about. This energy is called the activation energy. There's a lot of different symbols for it. EA is probably the easiest one to deal with. This is required to overcome a reaction barrier. Okay? And it turns out this guy controls the rate. So saying activation energy is a really key term. That's a really important thing. That activation energy, it will turn out, we'll talk more about this late in this lecture and next, that it has an enormously powerful influence on the rate of reaction. So in fact, a lot of what you're doing, right, the molecules in your body are messing with activation energies to control the rates of reaction, to make sure, for example, your lunch is digested today. Right? The other thing is, there's another energy up here. I guess I'll do that one in green. That energy from here to here, this is the overall energy. Okay? And this controls which direction is favored or unfavored. And that's another important thing for whether the reaction happens at all. So there's a bunch of important things I want to get from that. So did the bin make it all the way around? Where's the bin? Oh, it's making its way down. If you guys could see that it makes it down because I'm going to need it in like a minute or so. If you can just pass it down the edge of the aisle, it'll make its way back. Thanks, everybody. And I'm sorry you can't keep them. Bio department would kill me. And plus, it would look really weird on the front page of the Herald that I was giving away snap bracelets at the UMass Boston. It's hard to make that sound reasonable, even though it is. So, rate of reaction. There's a really important, this is another hugely important place where like the obvious answer turns out to be the wrong answer. And there's a really important thermodynamic pitfall. So we talk about the rate of a reaction. The rate of a reaction is not how fast each bracelet snaps, but it's how often bracelets snap. Oh, thank you very much. So the idea is the following. Let me straighten these guys out. We can simulate a little bit of a chemical reaction. We now know I'm loading up, it's sort of like, I don't know, TNT here, well, maybe it's not quite as powerful. I'm setting up, I'm putting in potential energy, getting this into the unstable state, right? If I straighten all these bad boys out. So what I can do is shake this. And if I do this hard enough, they'll snap. How come? I'm putting more energy in. If you're going to say physically, literally what happens to make them snap if I shake this? Pardon? They collide, exactly. If I shake this good and hard, a couple of them, yeah, it's hard to see from the back, but if they start to snap if you shake the box, all right? And the harder I shake, the more snap. Now, the way to look at this is the harder I shake, the faster the reaction goes. Now, does that mean that if I shake it hard, individual bracelets snap more quickly, go from straight to coiled more quickly? No. The time it takes to go from straight to coily is exactly the same whether I'm shaking gently or shaking hard. What happens is when I shake hard, in a minute or any time interval, more of them snap. And that's really important for chemical reactions because people think about like you heat it up, the chemical reaction happens faster. It does not mean that the atoms transform faster. It means in the population of atoms, more change in any given time interval. That happens more often. Okay, so it's not like you're running faster. It's like more people are running. All right. So let me write that up and say some things about that particular simulation because there's a bunch of important ideas there. So if I have three situations, number one, that was the box sitting still. And the rate is going to be 0. That I can let these, so for example, I straighten all of these out and I leave it in my office and it sits for 365 days until the next time I use it in my office. And none of them unkinked. I mean, none of them coiled up. So the rate sitting on my office is 0. And that corresponds to sort of the real world temperature where there's no motion, it's absolute 0. So at absolute 0, chemical reactions have a rate of 0. All chemical reactions have a rate of 0. Box shaking a little. The rate is low. And 3, the box shaking a lot. The rate is higher. And this is like warm and hot, right? So, and why does that happen? More shaking leads to more straight ones have enough energy to kink and then snap, leads to a faster rate. And again, to be really clear, an individual bracelet still takes the same amount of time to go from straight to coily. It's just, if I shake gently for a minute, say 3 or 4 of them would flip. If I shake hard for a minute, 20 or 30 will flip. All right? And that's the difference between those. That the rate of the reaction is how many molecules make the flip per second. Yeah, do you have a question? So here's that was actually going to be my very next thing, which was, oops, that was graceful. Can you make it go the other way? Right, if I shake this thing up. And so let me talk about that, because that's actually really important. So the question is, you might ask, can heating increase the rate of let me say it this way. I beg your pardon. Therefore, heating can increase the rate of a favored reaction. Okay? My question is this, which is akin to what you asked, is can heat make an unfavored reaction happen? All right? So, in the analogy of this, what's the unfavored reaction? Straightening out, right? What's the analogy of heat? Shaking. So how could you translate that into a question of what I do with this? So shaking hard, that is, the question is, shaking harder, can shaking harder make what happen? Straighten out, right? So the question is, if I shake this really hard, am I ever going to make them straighten out? No. Right? And why is that? Because the harder I shake, the more it's going to trigger them to snap. And then they go to their low energy state, and no matter how much heating I do, I'm never going to make them appreciably go straight again, because there's no way I can shake this hard enough to give them enough energy to straighten out. Right? And so that's another really important thing. That's why favored and unfavored are really are a big deal. The answer is no. That is, heat energy is not useful here. That is, more shaking will never make the coily ones go to be straightened out. That is, heat is random motion. And we need sort of specific energy to uncoil. So what I mean is this, and even if I could shake this hard enough to straighten some of them out, in an instant they would get knocked back to a coil. Because if I was shaking this so hard that they had enough energy to straighten out, well, that straight one is going to get whacked in a microsecond and coil back up again. So there's nothing I can do. I cannot win this battle by heating it. Right? I can make it coil as fast as I like. The harder I shake it, the faster it'll coil. But I can never make it go the other way. And so we'll talk about biological interpretations of that in the next couple of lectures. But before I go further, I want to make sure everybody's with me on that. What's going on there? You can't make it go from unstable to stable just by heating it. All right. So what I want to talk about now is try to get to move into the real chemistry of all this stuff. So the real thermo